Right now, as you're hearing these words, an alien visitor is racing through our solar system at 130,000 miles per hour, its ghostly green tail doing something that makes astronomers question the very laws of physics, pointing directly at our Sunday. Take a moment with me here. Let yourself truly arrive in this space we're creating together, because what we're about to explore isn't just another comet story. This is 3I Atlas, only the third confirmed interstellar object humanity has ever detected, and it's rewriting our understanding of what comets can do. Its atmosphere has swollen to half the diameter of our Sun, 348,000 kilometers of alien ice awakening after millions of years of frozen silence between the stars. Imagine a cosmic bubble so vast that Earth would fit inside it 27 times over, all erupting from a nucleus possibly just a few kilometers wide. And that impossible tail pointing sunward? That's just the beginning of its mysteries. So settle in wherever you are. Let the weight of your day fade into the background. We have time together to properly appreciate what's happening above our heads. Over the next while, we'll journey alongside this interstellar wanderer as it blazes through our cosmic neighborhood, carrying chemical fingerprints from another star system entirely. We'll discover why its carbon dioxide ice glows that eerie emerald green, why it brightened 1,000 times faster than any model predicted, and what its bizarre behavior might reveal about the alien solar system where it was born. This isn't just a story about a comet. It's about reading messages written in ice and light from stars we'll never see. But here's what keeps me awake at night. Why did it wait until precisely 2 astronomical units from our Sun to transform? What chemistry has been sleeping for eons, waiting for exactly this amount of warmth to explode into activity? Why does every measurement suggest this visitor is playing by rules we don't understand? And most haunting of all, what will happen during those crucial weeks when it swings closest to our Sun, hidden from Earth's view behind solar glare? September 2025 changed everything we thought we knew about comets. The first alerts began trickling in just after midnight, Greenwich Mean Time, spreading across the global astronomy network like ripples in a digital pond. Amateur astronomers in Chile noticed it first, then professionals in Hawaii confirmed what seemed impossible. Within hours, every major observatory on Earth had swiveled toward the same coordinates, chasing an object that was breaking the rules of cosmic behavior. 3I Atlas had awakened. Consider the scale of what happened that night. This interstellar visitor had been cruising through the darkness between stars for millions of years, its frozen chemistry locked in a state of deep hibernation. Then, at precisely 2 astronomical units from our Sun right around where Mars orbits, something triggered. The transformation was so sudden, so violent, that it caught every prediction model off guard. In less than 72 hours, the comet brightened from magnitude 15 to magnitude 12. Let me translate what those numbers mean for you. Magnitude 15 is invisible to all but the most powerful telescopes, a ghost of light barely distinguishable from the cosmic background. Magnitude 12 brings it within reach of serious amateur equipment, bright enough that dedicated skywatchers could spot this alien visitor with their backyard telescopes. That's a 1,000-fold increase in brightness. Picture a single candle flame suddenly blazing into a bonfire, and you'll begin to grasp the violence of this awakening. Dr. Sarah Chen was monitoring the automated surveys from Mauna Kea that night when the data streams started showing anomalies. The numbers climbing on her screen seemed wrong at first. Equipment malfunction, she assumed. Comets simply don't brighten this fast. The accepted models, built on decades of observations, suggested weeks or months for such dramatic changes. 3I Atlas accomplished it in days. The chemistry behind this explosion tells us something profound about where this visitor originated. When sunlight strikes ordinary comets from our solar system, their water ice sublimates gradually, creating those familiar tails we associate with cosmic wanderers. But 3I Atlas was different. Spectroscopic analysis revealed that carbon dioxide ice dominated its composition, with exotic carbon compounds that had never been exposed to anything warmer than the void between stars. These molecules had been assembled in the frigid nursery of an alien solar system, locked away for eons. At 2 AU, our Sun's warmth finally penetrated deep enough to trigger a cascade reaction. Picture frozen carbon dioxide suddenly finding enough energy to skip its liquid phase entirely, exploding directly from solid to gas. Now multiply that process across billions of tons of material, all happening simultaneously. The comet's coma. Its glowing atmosphere expanded from nothing to 348,000 kilometers in diameter, half the width of our sun, erupting from a nucleus we still can't properly measure. The most experienced comet observers found themselves recalibrating everything they thought they knew. Dr. Michael Tanaka at the Subaru telescope later described watching the real-time data. It was like watching geology happen at the speed of chemistry, processes that should take months compressed into hours. Every model we had was useless, but the brightness surge revealed something even stranger about our interstellar guest. The spectrum of light reflecting off 3I Atlas showed absorption lines that shouldn't exist in any comet from our solar system. These chemical fingerprints pointed to formation temperatures far colder than anything in our cosmic neighborhood temperatures, only possible in the outer reaches of a stellar system, very different from our own. The green glow that would soon captivate millions came from a specific molecular transition of diatomic carbon, energized by solar radiation in ways our local comets rarely display with such intensity. Think about being the first human to recognize what was happening. You're alone in an observatory, surrounded by the hum of cooling equipment and computer fans, when your instruments start registering something that violates everything in the textbooks. Your first instinct is disbelief. Check the calibration, run the diagnostics. But the numbers keep climbing, and slowly the realization sets in. You're witnessing an event that happens perhaps once in a civilization's lifetime. By dawn, observatories across 6 continents had confirmed the impossible. 3I Atlas wasn't just brightening, it was transforming in ways that suggested its very structure differed from anything born in our solar system. The anti-tail phenomenon, that ghostly finger pointing directly at our sun, emerged during this same period, adding another layer of mystery to an already baffling object. The implications rippled through the scientific community like shockwaves. If interstellar comets could behave this differently, what else had we assumed about these cosmic messengers? Every previous model, every careful calculation based on decades of observing our local comets, suddenly needed revision. 3I Atlas wasn't just visiting. It was teaching us how limited our perspective had been. But why 2 astronomical units? Why did this specific distance trigger such a violent awakening? The chemistry offers clues but not complete answers. At that distance, solar radiation reaches a critical threshold for certain exotic ices. Not warm enough to affect water ice significantly, but perfect for triggering carbon dioxide's explosive sublimation. Yet this explanation feels incomplete. Something about 3I Atlas's internal structure, perhaps layers of different ices arranged in ways our solar system never created, might have contributed to the precise timing. The comet's rapid brightening also hinted at something that would become clearer in the coming weeks. This wasn't a solid, monolithic object. Instead, 3I Atlas appeared to be more like a cosmic pile of rubble, loosely bound by its own weak gravity, with vast spaces between chunks of frozen material. As the carbon dioxide erupted, it didn't just create a tail. It began reshaping the comet itself, opening fissures and creating channels for even more dramatic outgassing. Each hour brought new surprises as material that had been locked away since before our sun was born finally met stellar warmth. The scale of this transformation defied every attempt at comparison. Earthbound analogies failed to capture what was happening 200 million kilometers away. This wasn't like ice melting or even dry ice sublimating in a laboratory. This was chemistry on a planetary scale, driven by forces we could observe but not fully comprehend. As September turned to October, 3I Atlas continued its inward plunge, growing brighter each night, that impossible anti-tail growing more pronounced. Soon it would pass inside Earth's orbit, venture closer to our sun than any interstellar object we'd tracked before. What new transformations awaited, as temperatures climbed even higher? What other exotic chemistry might awaken? The brightness surge was just the overture. The real performance was about to begin, and it would reveal that our mysterious visitor was larger, impossibly larger than anyone had dared imagine. But the brightness was just the first surprise. As astronomers worldwide trained their instruments on this interstellar visitor, The data revealed something that made them question their measurements. 3I Atlas wasn't just glowing, it was expanding into something monstrous. The numbers seemed wrong at first. Observatory after observatory reported the same impossible measurements, each team certain their equipment needed recalibration. The comet's coma, that glowing cloud of gas and dust surrounding its nucleus, had swollen to 348,000 kilometers in diameter, half the width of our Sunday. Dr. Elena Vasquez at the European Southern Observatory ran the calculations 4 times before accepting what she was seeing. This ghostly green bubble dwarfed Jupiter, our solar system's giant. Earth would fit inside it 27 times over, with room to spare. Yet all this magnificence erupted from a nucleus that might measure just a few kilometers across, a cosmic seed spawning an atmosphere visible from 100 million miles away. The scale defied comprehension. Our minds evolved to grasp human distances, the walk to work, the drive between cities, perhaps the flight across an ocean. 3I Atlas operated on dimensions that broke those mental frameworks. Its coma could swallow worlds. To understand what was happening, we need to journey from that tiny frozen nucleus outward through layers of alien chemistry. At the heart lies the solid core, a fragment of another star system, assembled from materials that condensed in temperatures we can barely imagine, colder than Antarctica's deepest winter, colder than the space between Earth and Moon. This ice formed in the outer darkness of an alien solar system, where even starlight arrives as a whisper. Now, solar warmth penetrates those ancient layers for the first time in millions of years. The effect resembles nothing in our earthly experience. Frozen carbon dioxide doesn't melt like water ice. It explodes directly from solid to gas, skipping the liquid phase entirely. Each square meter of the nucleus erupts with invisible violence, launching tons of material into space every second. The gas rushes outward at supersonic speeds, carrying dust particles that have slept since before our sun existed. Within minutes of leaving the surface, these molecules spread across thousands of kilometers. Within hours, they form that vast bubble we call the coma. The same physics that creates fog on a cold morning operates here, but multiplied by factors that strain belief. Standing on 3I Atlas's nucleus would mean death in seconds, but indulge the thought experiment. The ground beneath your feet wouldn't feel solid, more like compressed snow mixed with ash, held together by gravity so weak you could escape with a gentle jump. Jets of gas would erupt around you without warning, geysers of carbon dioxide powerful enough to reshape the landscape. The horizon would curve sharply on this tiny world, while overhead, the coma would glow with that distinctive green light, filtering the sun into an alien twilight. Moving outward from the nucleus, the environment changes dramatically every few kilometers. The inner coma seethes with fresh gas, still cold from its explosive birth. Dust particles collide and tumble, some clumping together, others spinning off into independent orbits around the comet. This is chemistry in motion, molecules breaking apart under solar radiation, recombining in patterns impossible in any laboratory. By 10,000 kilometers out, the density drops, but the spectacle intensifies. Here, solar wind begins its work, pushing gas and dust into those characteristic tails. But 3I Atlas breaks the rules even here. That anti-tail pointing sunward shouldn't exist according to our models, yet there it stretches, a finger of light aimed at our star like an accusation. The outer coma extends into realms where the word atmosphere loses meaning. Gas molecules here are so sparse that they rarely collide, each one following its own trajectory into space. Yet collectively, they catch and scatter sunlight, creating that ghostly glow visible across the solar system. This is matter in its most tenuous form, present enough to see, too thin to touch. Scientists studying this expansion faced a puzzle that deepened with each measurement. Comets from our solar system, even the spectacular ones, rarely achieve comas approaching this size. Hale-Bopp, that magnificent visitor from 1997, managed a coma roughly 1 million kilometers across at its peak, impressive by any standard, but still dwarfed by 3I Atlas. The difference lies in the chemistry. Our local comets formed in a disk of material already processed by our young Sunday. Their ices are primarily water, with traces of methane, ammonia, and other compounds we recognize. 3I Atlas carries the chemical signature of a completely different stellar nursery. Its carbon dioxide ice behaves differently under solar heating. Those exotic carbon compounds detected in its spectrum release energy in unfamiliar patterns. Dr. James Morrison at Caltech spent sleepless nights modeling the gas production rates. Traditional equations suggested the nucleus would need to be enormous, perhaps 50 kilometers across, to generate such a massive coma. But every other measurement pointed to something much smaller. The brightness variations, the rotation period barely detectable in the data, the way it responded to solar radiation, all suggested a nucleus no larger than a mountain. The paradox deepened when teams tried to measure the coma's mass. Despite its enormous volume, the total material in that vast bubble weighed less than a small asteroid. Spread across such distances, the gas achieved densities that made the space between planets seem crowded by comparison. You could fly a spacecraft through the coma and never collide with enough material to fog a window. This ghostly nature explained another mystery. As 3I Atlas approached the Sun, astronomers expected its massive coma to show distortions from solar wind pressure. Instead, it maintained its roughly spherical shape far longer than models predicted. The gas was simply too tenuous, too spread out for solar wind to sculpt it efficiently. 3I Atlas had created a bubble so vast and so empty that even the Sun struggled to reshape it. Modern technology allowed us to study this phenomenon with unprecedented detail. The Hubble Space Telescope captured images showing subtle color variations across the coma chemistry in action on a planetary scale. Radio telescopes detected emissions from specific molecules, mapping their distribution and movement. Spectroscopes broke down the light into chemical fingerprints more detailed than any cosmic visitor had revealed before. Each instrument told part of the story, but synthesizing the data required international collaboration. Teams in Japan tracked rotation signatures. European observatories monitored gas production rates. American facilities focused on the anti-tail mystery. Southern Hemisphere telescopes enjoyed the best viewing angles as 3I Atlas climbed through our skies. Never before had humanity brought such collective focus to a single cosmic object. The measurements revealed patterns that shouldn't exist. Gas jets on the nucleus activated and deactivated with a rhythm that suggested internal structure layers of different ices perhaps, or caverns that channeled eruptions in specific directions. The coma itself showed asymmetries that evolved hour by hour, vast currents of gas flowing in patterns too complex for our models to predict. But size was just one face of 3I Atlas's alien nature. As October progressed and the comet drew closer to our Sun, that characteristic green glow intensified beyond anything in the record books. The color itself held secrets about chemistry born around another star, waiting to reveal themselves as temperatures climbed toward their ultimate test. The first high-resolution images arrived at dawn on October 3rd, and they showed something no astronomer had prepared for. 3I Atlas wasn't just bright, it wasn't just massive. It was glowing with a green so intense that image processors initially flagged the data as corrupted. Dr. Kenji Nakamura at Subaru Telescope stared at his monitor, watching as the automated systems struggled to calibrate the color channels. The green dominated every spectrum, overwhelming the subtle blues and reds that should have been present in any comet's glow. This was chemistry, announcing itself across 100 million miles of space. The color was wrong. Not wrong in the sense of unexpected, but wrong in a way that made veteran observers check their equipment. Comets glow green, yes, but this particular shade, this specific wavelength signature, belonged to something else entirely. When sunlight strikes a typical comet from our solar system, water vapor dominates the show. The molecules break apart under solar radiation, creating hydroxyl radicals that emit a faint blue-green light. 3I Atlas played by different rules. Spectroscopic analysis revealed the green came primarily from diatomic carbon, those paired carbon atoms glowing at exactly 517 nanometers as solar energy ripped apart larger molecules. The chemistry told a story of alien cold. In our solar system, carbon dioxide ice forms only in the most frigid regions, far from our sun's warmth. Even there it exists as a minor component, overshadowed by water ice. 3I Atlas reversed that ratio completely. Dr. Maria Petrova at the European Southern Observatory ran the spectral analysis repeatedly, each time arriving at the same startling conclusion. Carbon dioxide dominated this comet's composition by a factor of 10. The exotic carbon compounds mixed throughout suggested formation temperatures below -220 degrees Celsius, colder than any natural environment in our solar system. The implications sent ripples through the astronomical community. This wasn't just a visitor from another star. This was a chemical time capsule, preserving the conditions of an alien stellar nursery. The green glow intensified hourly as 3I Atlas plunged sunward. By October 10th, amateur astronomers could detect the color through modest telescopes, that emerald radiance standing out against the star fields like nothing they'd seen. Professional observatories captured details that bordered on the surreal. Close examination revealed the green wasn't uniform. Brighter regions pulsed near the nucleus where fresh gas erupted most violently. The color faded gradually through the coma, shifting toward blue-green at the edges where different chemistry took hold. Jets of particularly intense green burst from active regions, painting streaks across the inner coma that evolved by the minute. To understand what created this alien light show, we need to descend into molecular physics. When a photon from our sun strikes a carbon dioxide molecule in the coma, violence erupts on the smallest scale. The molecule absorbs that energy, vibrating faster until the bonds between carbon and oxygen can't hold. The molecule flies apart. But the carbon atoms don't separate individually. They pair up, forming diatomic carbon, two atoms bound together in a configuration that barely exists on Earth. These paired atoms find themselves in an excited state, holding more energy than their structure prefers. Within nanoseconds, they release that excess as a photon of precisely 517 nanometers, pure green light. Multiply this process by trillions upon trillions of molecules every second, and 3I Atlas's coma becomes a vast green lantern, converting invisible solar radiation into that distinctive glow. The process feeds on itself. More sunlight means more broken molecules, which means more diatomic carbon, which means more green light. Dr. Hassan al-Rashid at Kitt Peak Observatory described watching the comet through the main telescope's eyepiece, a rare treat in our age of digital imaging. The green hit differently in person, he reported. Cameras captured the color accurately, but human eyes perceived something more visceral, a green that seemed to pulse with its own inner light. Several observers independently described the same sensation, as if the color carried information beyond mere wavelength. The comparison to Earth's auroras emerged naturally. Both phenomena involve excited atoms releasing specific wavelengths of light. But where auroras dance and flicker with Earth's magnetic field, 3I Atlas's glow emanated steadily from that enormous coma, powered by chemistry rather than magnetism. The green served as a beacon, announcing the presence of carbon compounds processed in ways our solar system never achieved. Laboratory attempts to recreate the exact shade failed consistently. Scientists could produce diatomic carbon's green emission, but something about the mixture, the ratios, the trace elements in 3I Atlas's chemistry created subtle variations that eluded duplication. The comet carried a recipe written in the conditions of another star. As October progressed, the green glow revealed structure within the coma that other wavelengths missed. Filaments of brighter emission traced the paths of major jets. Shells of varying intensity marked different generations of outgassing. The anti-tail showed its own green signature, slightly shifted in hue, suggesting different chemistry or temperature in that sunward-pointing anomaly. The most detailed spectroscopic studies uncovered traces of other carbon compounds contributing to the glow. Triatomic carbon added subtle variations. More complex molecules, some never synthesized on Earth, left their fingerprints in the light. Each discovery pointed to the same conclusion. 3I Atlas formed in an environment radically different from our cosmic neighborhood. Dr. Sarah Okafor at the South African Large Telescope coordinated a 24-hour observation campaign, tracking how the green emission varied with the comet's rotation. The data revealed that certain regions of the nucleus produced more intense color, suggesting uneven distribution of carbon dioxide ice. As these regions rotated into sunlight, Waves of green pulsed through the inner coma. The color served as more than mere spectacle. It provided a window into active chemistry happening in real time. Molecules that had remained frozen and inert for millions of years suddenly found themselves bathed in stellar radiation, breaking apart and recombining in patterns that lit up the darkness. The green glow marked zones of maximum chemical violence. Theoretical models suggested that as 3I Atlas approached perihelion, the green might shift toward blue as higher energy processes took hold. Water ice, if any existed beneath the carbon dioxide layers, would finally join the eruption. The color would tell the story of changing chemistry as temperatures soared. But the models failed to predict what observers noticed by October 15th. The green was intensifying beyond all calculations. Something about 3I Atlas's composition or structure accelerated the process in ways that challenged understanding. The answer might lie in those exotic carbon compounds detected early in the observations. Molecules unknown in our solar system could break down through intermediate stages, each producing its own contribution to the glow. The green we saw might represent not one process but dozens, all operating simultaneously at different depths within the coma. Public interest in the green comet soared as images spread across social media. The color photographed beautifully, that emerald glow standing out dramatically against the black of space. But the images only hinted at what those studying 3I Atlas were discovering. This wasn't just a pretty light show. This was chemistry from another star system, announcing itself in the most visible way possible. The green glow raised a fundamental question that haunted researchers. If 3I Atlas formed around a star very different from our Sun, what did that star look like? The chemistry suggested a cooler, redder star where carbon compounds could condense more readily than water. The exact ratios of different ices might encode information about stellar temperature, radiation environment, even the presence of planets that shaped the early solar system where our visitor was born. Night after night, the green beacon grew brighter. 3I Atlas was still weeks from its closest approach to our Sun, yet already it challenged every assumption about how interstellar comets should behave. The color that captivated millions served as a constant reminder that we were witnessing chemistry shaped by an alien star. Soon, that chemistry would face its ultimate test. As 3I Atlas dove deeper into our solar system, temperatures would climb toward levels that might shatter its frozen structure entirely. Would the green glow survive, or would new colors emerge as different layers of ice met solar heat? The answer waited in the coming weeks, as our interstellar visitor raced toward a rendezvous that would push matter to its limits. But first, that anti-tail pointing at our Sun demanded explanation. The green glow had shown us alien chemistry in action. The impossible tail would reveal alien physics. Then, observers noticed something impossible. A ghostly finger of light stretched from the comet directly toward our Sun, defying every law of comet physics written in textbooks across the world. Comet tails always point away from the Sun, pushed by solar wind and radiation pressure. Always, without exception, until 3I Atlas shattered that certainty with casual indifference. Dr. Roberto Silva at Cerro Tololo was reviewing the night's images when he spotted the anomaly. The tail pointed the wrong way. He cleaned his monitor screen, checked the image orientation, verified the coordinate system. The geometry remained unchanged. 3I Atlas displayed a luminous spike aimed directly at our star like an arrow seeking its target. Word spread through the astronomical community with electric urgency. Observers worldwide scrambled to confirm what couldn't be real. Hawaii, Chile, Australia, South Africa. Every telescope capable of resolving the comet's structure swung toward the same impossible sight. The anti-tail stretched across millions of kilometers, a brilliant contradiction to established physics. The next 72 hours would transform confident scientists into students again. Understanding why this violated physics requires grasping how normal comet tails form. When a comet approaches our Sun, frozen material sublimates into gas and releases embedded dust particles. Solar radiation and the stream of charged particles we call solar wind push this material away from the Sun, creating those familiar streaming tails. The physics are straightforward photon pressure, and particle collisions drive lightweight material outward, like smoke from a fire blown by steady wind. The direction never varies because the forces never reverse. Light radiates outward from our sundae, Solar wind flows outward from our Sunday. Therefore, comet tails must point outward from our Sunday. The logic seemed unassailable until 3i Atlas arrived to demonstrate our ignorance. The anti-tail appeared most prominent in photographs taken perpendicular to the comet's orbital plane. From Earth's vantage point that October, we viewed 3i Atlas slightly from above its trajectory. The normal tails. Yes, it had those two swept away from the sun as expected. But that additional spike of light jabbed inward, creating a cosmic compass needle pointing at our star's heart. Dr. Yuki Tanaka at Subaru Telescope dedicated an entire night to measuring the anti-tail's dimensions. The structure extended at least 15 million kilometers sunward, glowing with the same green light that dominated the coma but showing subtle spectral variations. The brightness fluctuated on timescales of hours, suggesting dynamic processes unlike anything in the normal tails. Close analysis revealed the anti-tail wasn't perfectly straight. It curved slightly, following a path that hinted at complex interactions between the comet's motion and whatever forces created this anomaly. The width varied too, narrowing and broadening in patterns that correlated with the comet's rotation period. Something about 3i Atlas's structure or composition channeled material in this impossible direction. The measurement teams worked around the clock, gathering data that might explain the phenomenon. Temperature readings showed no unusual heating that might create reverse flows. Magnetic field measurements detected nothing that could redirect charged particles against solar wind. The anti-tail existed in defiance of every force we understood. Graduate students found themselves thrust into the spotlight as their advisors grappled with the implications. Emma Chen at Caltech spent sleepless nights modeling particle trajectories, trying to find some combination of forces that could drive material sunward. Her simulations consistently failed. Virtual particles flowed away from the virtual sun, exactly as theory predicted. 3i Atlas ignored the simulations with serene indifference. The anti-tail's spectrum provided the first real clues. While dominated by the same diatomic carbon emission that colored the entire coma, careful analysis revealed an overabundance of heavier particles. Dust grains larger than typical cometary debris appeared concentrated in the sunward spike. These particles reflected sunlight differently, creating subtle color variations visible only through detailed spectroscopy. Dr. Mikhail Volkov at the Russian Academy of Sciences proposed a radical hypothesis. Perhaps we were seeing not a tail at all, but an optical illusion created by the comet's geometry. If 3i Atlas possessed an unusual shape elongated or doubled, the anti-tail might represent material in the orbital plane illuminated from a specific angle. The hypothesis crumbled when observations from different locations on Earth showed the same structure. This was no trick of perspective. So, the European Space Agency redirected observation time on their solar monitoring satellites, capturing 3i Atlas from angles impossible from Earth. The images arrived encrypted, precious data packets traveling hundreds of millions of kilometers. When decoded and processed, they showed the anti-tail even more clearly. From the L1 Lagrange point, with the sun at their backs, the satellites confirmed that material really was streaming toward our star. Panic is too strong a word for what rippled through the scientific community. Call it profound unease. If comets could violate this basic principle, what else might be wrong in our understanding? 3. Atlas had already demonstrated chemistry from an alien star system. Now it revealed physics that challenged fundamental assumptions. The International Astronomical Union convened emergency sessions, virtual meetings spanning time zones as researchers shared data and confusion in equal measure. Dr. Patricia Williams from MIT presented calculations showing that generating an anti-tail would require energy equivalent to a small nuclear reactor. Where was 3i Atlas getting this power? The sun's radiation fell far short of the necessary levels. Alternative explanations proliferated like startled birds. Some suggested electromagnetic effects from the comet's interaction with the solar wind might create temporary reversal zones. Others proposed that 3i Atlas carried metallic components that responded to our sun's magnetic field in unexpected ways. Each hypothesis met the same fate. The math didn't work. Dr. Li Wei at Beijing Observatory made a connection that shifted the discussion. Previous interstellar objects, Oumuamua and Borisov, had shown unusual properties, but nothing this dramatic. Perhaps the antitail revealed something fundamental about how matter behaved after millions of years in interstellar space. Cosmic ray bombardment might have created exotic ice structures that released energy in patterns our solar system never produced. The hypothesis gained traction as researchers modeled cosmic ray impacts on carbon dioxide ice over geological timescales. The radiation could create defects in the crystal structure, storing energy like a wound spring. When solar heating finally reached these modified layers, the stored energy might release in directed jets powerful enough to overcome solar pressure. But even this explanation felt incomplete. The antitail showed too much organization, too much consistency to result from random cosmic ray damage. 3I Atlas seemed to be following rules, just not rules we recognized. As October progressed, the antitail grew more prominent. Amateur astronomers posted images showing the structure visible through modest telescopes, that sunward spike becoming 3I Atlas's most distinctive feature. The media latched onto the mystery, with headlines proclaiming, "Impossible comet breaks laws of physics," and "Alien visitor defies science." The attention brought both opportunity and frustration. Public interest meant more funding for observations, but sensationalized coverage made serious scientific discussion harder. 3I Atlas became a cultural phenomenon, spawning conspiracy theories about alien technology and supernatural portents. Scientists found themselves defending basic physics while admitting they couldn't explain what everyone could see. Dr. Emilia Rodriguez, at Arecibo Observatory, coordinated radar observations, bouncing radio waves off the comet to map its structure. The returns showed something unexpected. The nucleus wasn't a single object, but possibly a collection of fragments held in loose formation. The gaps between fragments might channel outgassing in unusual directions, creating the antitail through purely mechanical means. The binary or multiple nucleus hypothesis explained some observations but raised new questions. How did these fragments maintain their formation across interstellar space? What kept them from drifting apart or colliding? The gravitational binding seemed too weak for such stability over millions of years. Fresh data arrived hourly as observatories worldwide maintained constant watch. The antitail showed variations synchronized with the comet's rotation, brightening and dimming with a period of approximately 12 hours. Certain orientations produced dramatic enhancements, as if invisible nozzles were directing material sunward during specific parts of the rotation. The phenomenon forced a reconsideration of basic assumptions. Perhaps antitails were more common than believed, just too faint to detect in normal comets. 3I Atlas, with its extreme chemistry and massive coma, might simply make visible what usually remained hidden. Researchers began re-examining archived images of other comets, searching for hints of similar structures. Dr. Fernando Mendez at La Silla Observatory discovered historical observations from the 19th century, describing comets with anomalous appendages pointing toward the Sunday. The reports had been dismissed as observational errors, but 3I Atlas cast new light on these old records. Perhaps antitails appeared periodically throughout history, challenging each generation of astronomers before being forgotten or explained away. The mystery deepened when spectroscopic analysis revealed the antitail contained molecules not present in the regular tails. Complex carbon chains, some with structures resembling organic compounds, appeared concentrated in the sunward stream. These molecules should have been destroyed by solar radiation, yet they persisted and even seemed to thrive in the antitail environment. Computer models grew increasingly complex as teams tried to account for every observation. The University of Tokyo's supercomputer ran simulations incorporating exotic physics, negative radiation pressure, gravitational anomalies, even speculative dark matter interactions. Nothing reproduced 3I Atlas's behavior. The comet remained stubbornly impossible. By late October, the antitail dominated 3I Atlas's appearance. The structure had grown to 20 million kilometers in length, rivaling the normal dust tail in brightness. Time-lapse animations showed the antitail writhing like a living thing, responding to forces that remained invisible and incomprehensible. The closer 3I Atlas approached our Sun, the more prominent its impossible tail became. Whatever process drove material sunward seemed to intensify with increasing solar radiation, exactly opposite to conventional physics. The paradox deepened with each measurement. Some researchers began to wonder if the anti-tail might represent our first glimpse of truly alien physics. If 3I Atlas formed in a stellar system with different fundamental constants or exotic matter distributions, it might carry those conditions within its structure. The anti-tail could be matter responding to rules written in another part of the universe. As November approached, 3I Atlas would soon pass behind the Sun from Earth's perspective, entering a period where ground-based observations would become impossible. The anti-tail mystery might remain unsolved, another cosmic enigma added to astronomy's growing collection. Unless space-based observatories could maintain coverage during those crucial weeks, we might never understand what drove matter toward our star against every known force. But 3I Atlas hadn't finished revealing its secrets. The anti-tail was just one piece of a larger puzzle. Soon, observers would discover that this interstellar visitor didn't just break the rules of physics. It might be carrying evidence of its birthplace encoded in ratios of molecules that shouldn't exist. The story of where 3I Atlas came from would prove even stranger than its impossible tale. To understand 3I Atlas, we must journey back millions of years, before our sun existed, before Earth formed, to a stellar nursery unlike anything in our cosmic neighborhood. Stars birth comets like afterthoughts. While the main stellar furnace ignites at a nebula's heart, leftover material swirls in vast disks, gradually condensing into planets, asteroids, and at the frozen edges, comets. 3I Atlas began its existence in such a disk, but one fundamentally different from the cloud that created our solar system. The evidence hides in those impossible chemical ratios our spectrographs detected. Carbon dioxide ice dominates where water should reign. Exotic carbon compounds exist in proportions that require formation temperatures even our outer planets never experienced. This comet condensed in a place where physics operated under subtly different conditions. Dr. Yuki Tanaka spent weeks analyzing the spectral data, each measurement revealing new impossibilities. The isotope ratios told a story of stellar nucleosynthesis following unfamiliar patterns. Carbon-13 appeared in abundances, suggesting formation near a star that burned cooler and slower than our Sunday. The mathematics pointed to a red dwarf, those dim stellar embers that comprise 70% of our galaxy's stars. Red dwarfs create different environments than our yellow Sunday. Their feeble warmth extends barely far enough to sustain planets. Beyond that meager heat, temperatures plunge to levels where carbon dioxide freezes before water, where exotic chemistry flourishes in the endless cold. 3I Atlas carries the signature of such a birthplace in every molecule. The formation process itself would have stretched across millennia. In that alien disk, microscopic grains of dust served as seeds for condensation. Carbon dioxide molecules, drifting through the void at speeds measured in centimeters per second, collided with these grains and stuck. Layer by layer, the comet grew from dust speck to pebble to boulder to mountain. But something unusual happened during those ancient aggregations. The layers didn't form uniformly. Dr. Maria Petrova's analysis revealed structures suggesting periodic interruptions, as if the comet's growth stopped and started repeatedly. Perhaps the young star experienced fluctuations, warming and cooling in cycles that left their mark in the ice. Or gravitational disruptions from forming planets stirred the disk, creating waves of compression and rarefaction. The result was a cosmic layer cake of different ices and trapped gases, each stratum recording conditions at the time of its formation. When our sun's heat finally penetrated these layers billions of years later, they would respond differently, creating the spectacular outgassing we witnessed. The anti-tail mystery might trace back to these primordial variations. The journey from that alien stellar system to ours defies comprehension in its scope. 3I Atlas didn't simply drift away from its parent star. Something violent ejected it, launching this fragment of frozen chemistry into the void between stars. The possibilities narrow to a few dramatic scenarios. A close encounter with a forming gas giant could have provided the gravitational slingshot. As the young planet swept through the outer disk, its gravity would have scattered countless comets. Most fell sunward or achieved new orbits, but a precious few, approaching at just the right angle with just the right velocity, escaped entirely. 3I Atlas was one of these lucky outcasts. Or perhaps the drama came from the star itself. Red dwarfs, despite their seeming calm, experience powerful flares that can strip atmospheres from close-in planets. A particularly violent stellar eruption might have provided the push, radiation pressure accelerating lightweight comets beyond escape velocity. The same carbon dioxide ice that now created such spectacle would have acted as a sail, catching stellar wind and riding it into interstellar space. The third possibility seems almost too perfect. Another star, drifting past the young system, could have gravitationally disrupted the outer comet cloud. Such stellar encounters happen rarely, but in the crowded stellar nurseries where stars are born, close passes occur more frequently. 3I Atlas might have been torn from its home by a celestial thief that vanished into the night. Whatever the cause, our comet found itself alone in the darkness between stars, beginning a journey that would last longer than complex life has existed on Earth. The initial velocity determined everything that followed. Too slow, and gravity would have reclaimed it. Too fast, and it would have shot past our solar system unnoticed. 3. Atlas travelled at precisely the speed needed to eventually fall into our sun's gravitational embrace. The interstellar journey itself shaped the comet in ways we're only beginning to understand. Out there, between the stars, conditions exceed anything we can properly imagine. The temperature hovers just degrees above absolute zero. No stellar wind stirs the emptiness. Cosmic rays provide the only activity, high-energy particles striking the comet's surface and penetrating deep into its structure. For millions of years, these cosmic rays bombarded 3I Atlas, creating chemical changes impossible in any other environment. Dr. Chen's models suggested the radiation created a crust of modified ice, chemically altered and structurally transformed. This processed outer layer might explain the explosive awakening when solar heat finally arrived. The cosmic rays had wound a spring that waited eons to release. The isolation was absolute. No starlight beyond the faintest glimmer from distant suns. No warmth beyond the negligible heat from radioactive decay within dust grains. No activity beyond the slow sublimation of the most volatile compounds, creating a gossamer-thin atmosphere that immediately escaped to space. 3I Atlas slept through the rise and fall of species, the birth and death of stars, the slow dance of galaxies. Navigation through interstellar space follows no paths. The comet tumbled randomly, its rotation gradually changing as asymmetric outgassing provided tiny torques. Without stellar radiation to drive sublimation, even these minimal forces could alter its spin over millions of years. The 12-hour rotation period we measured might have been established during this lonely journey, a cosmic accident that would later synchronize with the anti-tail's behavior. The darkness preserved everything. Unlike comets in our solar system, repeatedly baked by solar passages, 3I Atlas remained pristine. Every molecule stayed locked in place, waiting. The exotic compounds detected in our spectroscopes survived because nothing disturbed them. This was chemistry in deep freeze, a sample collection from an alien star delivered across impossible distances. The approach to our solar system began subtly. At first, just a slight deviation from straight-line motion as our sun's gravity made itself felt across the light years. The deflection accumulated slowly, bending 3I Atlas's path into a hyperbolic arc. By the time it crossed Neptune's orbit, destiny was sealed. The comet would make one passage through our solar system before escaping forever, but that single passage would reveal secrets hidden since before our world existed. As 3I Atlas fell sunward, each million-kilometer milestone brought new temperatures, new chemistry, new revelations. The preserved layers began their sequential awakening, each one telling part of the story of an alien stellar system. The transition from interstellar space to solar system happened gradually, then suddenly. Beyond Neptune, little changed. The sun remained just another star, slightly brighter than the rest. But as 3I Atlas crossed inside Uranus's orbit, transformation began. Solar wind, absent for millions of years, started its work. Photons carrying actual warmth struck ice that had known only cosmic cold. The first subtle changes appeared in the spectroscopic data months before the dramatic awakening at 2 astronomical units. Trace gases, frozen beyond detection, began their escape. The comet developed the faintest imaginable coma, visible only to our most sensitive instruments. These early emissions carried chemical signatures that would later help decode the comet's history. By Jupiter's orbit, 3I Atlas had become a solar system object, fully caught in our sun's influence. The hyperbolic trajectory meant this capture was temporary, but for these precious months, an alien artifact would submit to our star's examination. Every instrument humanity could aim skyward would extract secrets from this messenger. The preservation wasn't perfect. Those cosmic rays that created the modified crust also destroyed information. Complex molecules broke into simpler components. Isotope ratios shifted slightly, but enough remained intact to read the comet's history like a damaged book with most pages still legible. Each observation added words to the translation. Dr. Sarah Okafor compared the process to archaeology, but reversed. Instead of digging down through layers of history, astronomers watched as 3I Atlas unveiled its past from inside out. The heat penetrated deeper with each passing day, reaching strata laid down at different times under different conditions. The November perihelion would mark the deepest excavation, potentially exposing material from the comet's very birth. The alien system clues emerged not from any single measurement, but from the accumulation of impossibilities. The carbon dioxide to water ice ratio was just the beginning. Methane appeared in forms suggesting catalysis by minerals absent from our solar system. Noble gases trapped in the ice matrix showed abundance patterns requiring a stellar environment with different ultraviolet output. Most intriguing were the organic compounds. Not life, no one was suggesting that, but complex carbon chains assembled in patterns that spoke of unique chemistry. Dr. Mikhail Volkov described them as jazz variations on familiar themes. The same carbon, hydrogen, oxygen, and nitrogen, but arranged according to different compositional rules. These molecules told stories of chemical evolution in an alien laboratory. The parent star gradually revealed itself through these molecular testimonies. Definitely a red dwarf, but one with peculiar characteristics. The lithium abundance suggested an older star, perhaps 8 or 9 billion years old. The metallicity astronomers' term for elements heavier than helium pointed to a star formed later in the universe's history, enriched by generations of supernovae. This created a paradox. 3I Atlas itself couldn't be that old. Comets don't survive billions of years of storage, even in interstellar space. The gradual escape of volatile compounds, the accumulation of cosmic ray damage, the simple mechanical stresses of rotation would destroy such fragile objects. Our visitor was probably mere millions of years old when it began its interstellar journey. The resolution came from considering stellar evolution. The red dwarf birthed 3I Atlas relatively recently in cosmic terms, perhaps a billion years ago. The comet formed, was ejected, and wandered for millions of years before arriving here. Its parent star continued burning slowly, barely changing over such short timescales. Somewhere in our galaxy, that dim red sun still shines, perhaps still surrounded by comets identical to our visitor. Dr. Patricia Williams calculated probable trajectories backward, trying to identify 3I Atlas's home. The mathematics yielded a cone of possibility rather than a precise origin, too many variables accumulating over such vast times and distances. But the general direction pointed toward the galaxy's inner regions, where older stars congregate. Our visitor came from deeper within the Milky Way's disk, carrying news from regions where stars pack more densely. The chemical messages encoded more than just stellar characteristics. Patterns in the mineral content suggested planetary formation in that alien system. Large planets must have stirred the disk, creating pressure waves that concentrated certain materials. The presence of specific silicates pointed to rocky world formation closer to the star. 3I Atlas witnessed the birth of an entire solar system before its exile. As November approached and perihelion loomed, astronomers prepared for the deepest revelations. The innermost ice layers, those first deposited around dust grains in an alien stellar nursery, would finally meet our sun's heat. What final secrets would emerge as temperatures soared beyond anything 3I Atlas had experienced since birth? The poetry of the situation struck many observers. Here was humanity, confined to one small world, reading messages written before our planet existed. Each spectral line connected us to processes occurring around other stars. Every impossible molecule reminded us that chemistry follows different paths in different places. 3. Atlas served as proof that material constantly flows between stellar systems, that the galaxy churns and mixes its contents over cosmic time. We stood at a unique moment. For all of human history, comets came and went as mysteries. Only in the last few decades had we developed instruments capable of reading their chemical stories. And only now, with 3I Atlas, did we have a confirmed messenger from another star to decode. The coincidence felt almost orchestrated, as if the universe had waited until we were ready before delivering this interstellar letter. But time was running out. 3I Atlas approached its solar rendezvous, after which it would recede forever beyond our reach. The anti-tail still defied explanation. The chemistry still held secrets. And most concerning of all, the comet showed signs of structural instability that suggested it might not survive its closest approach intact. The journey that began around an alien sun billions of years ago was approaching its climax in our solar system. Whatever happened next would write the final chapter in this cosmic odyssey. 3I Atlas had traveled between stars to deliver its messages. Whether humanity could decode them in time remained uncertain. The December 27th discovery changed everything. Atlas telescope operator David Morris had been monitoring routine near-Earth asteroid surveys from Mauna Loa when his screens registered an anomaly moving against the star field. The automated detection system flagged it as a potential comet, but the trajectory calculations made no sense. This object wasn't orbiting our sun, it was passing through. Morris ran the orbital elements 3 times before calling his supervisor. The numbers remained impossible each time. The object's path traced a perfect hyperbola, mathematical proof that it came from beyond our solar system. Within 6 hours, confirmatory observations from telescopes across the Pacific had verified what seemed like science fiction. Humanity had discovered its 3rd confirmed interstellar visitor. The designation came swiftly, 2024/3I/Atlas. That simple alphanumeric code marked a cosmic milestone. Only twice before had astronomers confirmed objects from other star systems passing through our neighborhood. Oumuamua in 2017, Borisov in 2019. Now Atlas joined this exclusive catalogue, but it would soon prove far stranger than its predecessors. Dr. Jennifer Park at Gemini Observatory coordinated the early tracking efforts. The initial measurements suggested something remarkable. This visitor was still far from our sun, giving astronomers unprecedented lead time to prepare. Unlike Oumuamua, discovered as it was already leaving, Atlas approached from a perfect viewing angle. Every major observatory on Earth could track its inbound journey. The naming process followed established protocols but carried special weight. 3I meant 3rd interstellar object, a designation that would enter history books. Atlas honored the Hawaiian telescope system that first spotted this cosmic wanderer, but names barely captured what this discovery represented. Each interstellar object offered a keyhole glimpse into alien solar systems, carrying chemical and physical evidence from stars we would never visit. Initial spectroscopy revealed the first hints of Atlas's alien nature. Where comets from our solar system showed familiar signatures of water, ice, and common minerals, Atlas displayed absorption lines that sent researchers scrambling to their reference libraries. Carbon dioxide dominated where water should reign supreme. Exotic carbon chains appeared in ratios that required formation in environments our solar system never provided. Dr. Michael Chen at Keck Observatory described the early confusion. Every measurement contradicted our expectations. The spectral signatures looked like someone had scrambled the periodic table. We kept rechecking our instruments, convinced something was wrong with the calibration. But the data was solid. Atlas simply didn't match anything in our catalogues. The size estimates triggered the first wave of disbelief. Based on its brightness at such extreme distance, Atlas appeared massive, potentially the largest comet nucleus ever detected. But the brightness variation suggested something else entirely. This wasn't a solid mountain of ice. The irregular light curves hinted at a loosely bound collection of fragments, perhaps held together by the weakest of gravitational embraces. As news of the discovery spread through the International Astronomical Union's alert network, observatories worldwide pivoted toward the same coordinates. Southern Hemisphere facilities enjoyed the best viewing angles, turning Atlas into the most observed object in the sky. The data poured in faster than teams could process it, each measurement adding new mysteries to an already baffling visitor. The historical context made this discovery even more precious. Oumuamua had been spotted too late, already racing away from our sun when telescopes found it. Its rocky nature and bizarre acceleration defied easy explanation, leaving more questions than answers. Borisov proved more cooperative, clearly a comet, but one carrying chemistry from another star. Now Atlas promised to exceed both predecessors in scientific value. Dr. Lisa Yamamoto at Subaru Telescope emphasized what made this opportunity unique. Atlas gave us something we'd never had before time. Months to prepare, to coordinate, to develop new observation strategies. When you're studying something from another star system, every photon counts. This time, we could maximize our data collection. The early observations revealed Atlas wasn't just chemically exotic, it was dynamically unusual. Most comets from our Oort cloud fall toward the Sun on long elliptical orbits, taking centuries or millennia to complete each circuit. Atlas followed a hyperbolic path that would bring it close to our star exactly once before ejecting it back into interstellar space forever. The mathematics were unforgiving. We had one chance to study this visitor. Professional astronomers weren't the only ones mobilizing. Amateur observers with sophisticated equipment began their own monitoring campaigns. Online forums buzzed with discussion of optimal viewing times and techniques. Atlas became a global collaborative project, uniting observers across continents in common purpose. The comet didn't care about national boundaries or academic rivalries. It offered its secrets equally to anyone with eyes to see. The early chemical analysis yielded a revelation that shifted the entire investigation. The carbon isotope ratios in Atlas's spectrum didn't match any solar system object. These ratios, set during formation, served as fingerprints of the environment where the comet condensed. Atlas carried the signature of a stellar nursery with different initial conditions, different chemistry, different physics than the cloud that birthed our Sunday. Dr. Roberto Silva spent sleepless nights modeling what kind of star could produce such isotope patterns. The calculations pointed toward a red dwarf, one of those dim stellar embers that make up most of our galaxy. But not just any red dwarf. This one had peculiar metal abundances, suggesting it formed from material enriched by multiple generations of supernovae. Atlas hadn't just come from another star. It came from an older part of the galaxy where stellar evolution had progressed further. The discovery timing felt almost miraculous. 20 years earlier, we lacked the instruments to properly study such an object. 20 years later, who knew if humanity would still maintain the global cooperation necessary for this kind of research? Atlas arrived at the perfect moment, when our technology and organization could extract maximum scientific value from its passage. But the real drama was just beginning. As Atlas fell deeper into our solar system, solar heating would awaken chemistry that had slept since before Earth existed. The predictions varied wildly. Conservative models suggested a typical cometary display, just with unusual composition. Extreme scenarios painted pictures of explosive outgassing that could fragment the nucleus entirely. Nobody knew which future awaited. The mobilization intensified as Atlas crossed Neptune's orbit. Space agencies diverted observation time from scheduled programs. University departments reorganized research priorities. Funding that usually took years to approve materialized in weeks. The entire astronomical community recognized this opportunity might not repeat in their lifetimes. Every decision carried the weight of historical judgment. Dr. Patricia Williams coordinated the American response. We approached it like a space mission, except our spacecraft was the entire planet Earth. Every telescope became an instrument, every observer a mission specialist. The coordination challenges were staggering, but the alternative was unthinkable. We couldn't waste this chance. The early brightness measurements added urgency to the preparations. Atlas was brightening faster than models predicted, suggesting either a massive nucleus or extreme volatility. If the brightening continued at this rate, the comet would become visible to amateur telescopes months ahead of schedule. The public would soon join professional astronomers in watching this interstellar visitor's approach. International cooperation reached levels rarely seen outside crisis response. Data sharing agreements that normally took months of negotiation were settled in days. Proprietary analysis software became freely available. Language barriers dissolved as researchers found common ground in mathematics and physics. Atlas had united humanity's observers in ways politics never could. The Japanese team at Subaru Observatory made a discovery that explained some early mysteries while deepening others. Atlas wasn't rotating smoothly. The light curve showed complex patterns suggesting either a highly irregular shape or multiple components tumbling in loose formation. This complicated every observation, as different faces of the comet presented different chemistry to our instruments. The object refused to be simple. As October arrived, Atlas had become the most studied object in the solar system. Terabytes of data flowed daily from observatories worldwide. Machine learning algorithms churned through the measurements, seeking patterns human eyes might miss. Graduate students found their thesis projects revolutionized overnight. Established professors rewrote decades of assumptions. Atlas was reshaping astronomy in real time. The green glow first appeared in late October images, faint but unmistakable. This wasn't the blue-green of normal comets, but something more vivid, more alien. Spectroscopy revealed the color came from diatomic carbon fluorescing under solar radiation, but the intensity exceeded anything in terrestrial laboratories. Atlas glowed with the light of chemistry born under an alien sunday. Public interest exploded as the first color images circulated online. Atlas wasn't just another space rock. It was beautiful, haunting, impossible to ignore. The media struggled to convey the significance without sensationalizing. How do you explain to a general audience that they're seeing light from molecules assembled around another star? That the green glow carried messages from a stellar system that might no longer exist? The organization required for continuous observation pushed international cooperation to new heights. As Earth rotated, different observatories took over tracking duties, creating an unbroken chain of data. When weather blocked one site, others compensated. When equipment failed, backup systems activated. Humanity had created a planet-wide instrument focused on a single target. But it was the anti-tail discovery that transformed Atlas from remarkable to revolutionary. That ghostly finger pointing directly at our sun shattered decades of comfortable assumptions about comet physics. The images were unambiguous material streaming toward our star, not away from it. The observation teams checked and rechecked, but the impossible geometry remained. Atlas had arrived to overturn textbooks. Dr. Yuki Tanaka remembered the moment. We stared at the screen in silence. Everyone in the control room knew what we were seeing violated basic physics, but there it was, clear as could be. Atlas had an anti-tail pointing at the sunday. In that moment, we realized this visitor would teach us more than we imagined. The discovery of Atlas marked more than just another catalog entry. It announced that our solar system regularly received visitors from other stars, each carrying chemical messages from distant stellar systems. The universe had revealed itself as more connected, more dynamic than we dared imagine, and Atlas was just beginning to tell its story. As November approached, the real show would begin. Solar heating would penetrate deeper into Atlas's frozen heart, awakening chemistry preserved since its formation. Would it survive the passage, fragment into pieces, reveal even greater mysteries? The astronomical community held its breath, instruments ready, as humanity's third confirmed interstellar visitor raced toward its solar appointment. The greatest discoveries still lay ahead. At 130,000 miles per hour, 3I Atlas tears through space faster than any human mind can properly grasp. The mathematics are simple, the comprehension is impossible. This frozen fragment of another star system covers the distance from New York to Los Angeles in 67 seconds, Earth to Moon in under 2 hours. By the time you finish hearing this sentence, Atlas has traveled another 1,000 kilometers closer to our sunday. Dr. Elena Vasquez at Paranal Observatory calculated the trajectory until her eyes burned from staring at screens. The hyperbolic path curved through their charts like a cosmic slingshot drawn by an invisible hand. Every measurement confirmed the same truth. Atlas would get exactly one chance at our solar system before mathematics and momentum carried it back to the darkness forever. The speed transforms everything about how we study this visitor. Normal comets lumber through their orbits at velocities that grant astronomers years of observation. Halley's Comet crawls past at a mere 35,000 miles per hour during its fastest approach. Hale-Bopp managed 44,000. Atlas races nearly 3 times faster, compressing decades of typical observation into mere months. This velocity comes from the deepest reaches of interstellar space. Unlike our local comets, which orbit endlessly around the Sun, Atlas carries the momentum of its ancient ejection from another stellar system. Millions of years of travel have barely slowed it down. Our Sun's gravity bends its path but cannot capture it. The same speed that brought Atlas here ensures it will leave. Dr. Kenji Nakamura tracked the acceleration curves as Atlas plunged deeper into our gravity well. The numbers climbed relentlessly: 135,000 miles per hour, 140,000. Each day brought incremental increases as our Sun pulled harder on this interstellar wanderer. By perihelion, Atlas would reach 170,000 miles per hour, nearly 3 times highway speed every single second. The observation windows contracted with each passing week. At such velocities, Atlas crossed telescope fields of view in minutes rather than hours. Tracking systems designed for leisurely solar system objects strained to keep pace. Mount motors whined in protest as they swiveled at maximum speed. Software crashed under computational loads never anticipated. Atlas demanded engineering solutions invented on the fly. Amateur astronomers discovered the challenge firsthand. Marcus Thompson in Arizona managed to capture Atlas in his 14-inch telescope, but keeping it centered proved nearly impossible. The comet drifted across his eyepiece like a ghost refusing to be pinned down. By the time he adjusted the tracking, Atlas had moved beyond recovery. The speed turned observation into a race that human reflexes could barely win. The velocity affected spectroscopy most dramatically. Light from a moving object shifts in wavelength, the Doppler effect that astronomers use to measure cosmic motions. But Atlas moved so fast that standard correction algorithms failed. Every absorption line appeared displaced from its expected position. Teams spent precious hours recalibrating their instruments, compensating for speeds that pushed measurement techniques to their limits. Dr. Sarah Chen described the frustration of those early attempts at chemical analysis. The spectral lines wouldn't stay still long enough for clean readings. Carbon dioxide signatures blurred into carbon monoxide. Exotic molecules hid behind velocity-induced distortions. Atlas kept its chemical secrets wrapped in the armor of its own speed. The hyperbolic trajectory told its own story through mathematical poetry. That perfect curve drawn through space spoke of origins beyond our Sun's influence and destinations we would never know. Unlike the closed ellipses of solar system comets, Atlas followed an open path. No amount of time would bring it back. This passage marked both hello and goodbye forever. At mission control rooms worldwide, trajectory specialists ran simulations with growing urgency. The speed meant critical observations had to be scheduled with military precision. Miss your window by minutes, and Atlas would have moved beyond optimal viewing angles. Delay a spectroscopic run by an hour, and different chemistry would face your instruments. The entire comet changed its presented face faster than teams could document. The acceleration wasn't constant. As Atlas approached our Sun, gravity's pull strengthened according to Newton's ancient equations. But the relationship between distance and speed followed curves that challenged human intuition. Halving the distance meant doubling the gravitational force. The final plunge would happen so fast that blink and you'd miss crucial transformations. Dr. Patricia Williams coordinated observation schedules that resembled battle plans more than scientific programs. Each telescope received precise timing windows. Every instrument knew exactly when to activate. The margin for error shrank with each passing day. Atlas wouldn't wait for equipment failures or weather delays. Its schedule was written in orbital mechanics that brooked no deviation. The speed revealed itself in subtle ways throughout the data. Time-lapse animations showed Atlas racing past background stars like a Formula One car passing parked vehicles. While other celestial objects crawled across the sky in stately procession, Atlas blazed its own trail. The motion was visible night to night, even hour to hour as perihelion approached. Public communication about the speed proved challenging. How do you convey velocities that exceed human experience? News outlets tried various comparisons. Faster than the fastest rocket. Quick enough to circle Earth in 18 minutes. But numbers failed to capture the visceral reality of an object moving at cosmic drag racing speeds through our peaceful solar system. The velocity added urgency to every observation. Each spectrum captured chemistry that would never repeat at that exact distance from our Sunday. Every image froze a moment that passed instantly and irrevocably. The usual luxury of repeated measurements vanished. Atlas offered one chance at each data point before racing onward to the next revelation. Space agencies calculated intercept trajectories out of curiosity more than possibility. To match Atlas's speed would require rockets beyond current technology. Even reaching a fraction of its velocity would demand multi-stage vehicles and gravitational assists from multiple planets. Humanity could only watch as this visitor blazed past, too fast to touch, too quick to follow. The psychological impact on observers grew as the speed became personal. Dr. Mikhail Volkov described dreams where Atlas whooshed past too quickly to see clearly. Other astronomers reported similar experiences. The comet had invaded their subconscious, its velocity becoming a source of anxiety. So much to learn, so little time, and Atlas racing away faster each day. By early December, the effects of speed dominated every aspect of the observation campaign. Exposure times shortened to prevent motion blur. Tracking algorithms updated hourly. Communication networks strained to share data before it became obsolete. The entire global effort raced against Atlas's relentless momentum. The Hubble Space Telescope, free from atmospheric interference, managed the clearest tracking shots. But even Hubble's sophisticated systems struggled with Atlas's pace. Engineers uploaded new software daily, each patch addressing problems discovered in the previous night's observations. The comet had turned humanity's finest instruments into students learning new lessons at breakneck speed. Ground-based adaptive optics systems pushed beyond design specifications. The deformable mirrors that corrected for atmospheric turbulence now also compensated for Atlas's motion. Laser guide stars helped maintain lock, but the comet's speed meant constant recalibration. Every successful observation represented a minor miracle of engineering and determination. The speed differential between Atlas and Earth created unique viewing geometries. As our planet orbited the Sun at 67,000 miles per hour, Atlas screamed past at more than twice that velocity. The relative motions meant viewing angles changed dramatically week to week. Southern Hemisphere observatories enjoyed advantages that shifted to northern facilities as celestial mechanics played out. Dr. Lisa Yamamoto calculated that Atlas would cross the entire span of our solar system from Neptune to Mercury in less than 9 months. For comparison, Voyager 2 took 12 years to make a similar journey. The mathematics emphasized how briefly this interstellar visitor would grace our skies. Every lost observation opportunity meant information vanished forever into the darkness between stars. The velocity imposed hard deadlines on every research question. Would Atlas fragment during perihelion? The answer would arrive in weeks, not years. How would its exotic chemistry respond to maximum solar heating? No time for careful preliminary studies. Every question demanded immediate investigation because Atlas wouldn't pause for human convenience. Professional astronomers weren't alone in feeling the pressure. Amateur observers organized relay networks, passing tracking data across time zones as Earth rotated. When Atlas set in Japan, Australian observers picked up coverage. European telescopes took over from African sites. The speed had united observers in a race against cosmic motion itself. As December progressed, the acceleration continued its relentless climb. 150,000 miles per hour, 155,000. The numbers lost meaning, except as markers of how quickly their subject would escape. Atlas hadn't come to visit, it had come to demonstrate the temporary nature of all cosmic encounters. The speed would peak at perihelion, that closest approach to our Sun where Atlas would slingshot around our star at velocities that mocked human ambition. Then, just as quickly, It would begin the long deceleration toward interstellar space. But it would never slow enough for our sun to capture it. The mathematics were absolute. Atlas would leave us, carrying its remaining secrets back to the void. Every measurement now carried the weight of permanence. This spectrum, this image, this data point would be all humanity ever gathered from this particular angle, this specific distance, this exact moment. The speed transformed routine observations into historical documents. Future generations would study what we recorded because they would never get their own chance. Dr. Roberto Silva summarized the community's mood in those racing December days. We felt like archaeologists, given 20 minutes in an intact pyramid before it vanished forever. Every choice matters. Every second counts. And the clock never stops ticking. But speed was just one dimension of Atlas's challenge to human understanding. As the comet raced inward, its destiny became clearer. Soon, it would disappear behind our sun, hidden from Earth's view during the most critical phase of its journey. What would happen during those lost weeks remained a mystery that velocity would snatch away before we could solve it. The cosmic race continued, with Atlas winning by margins measured in physics rather than desire. The universe had prepared its cruelest joke for the astronomers who'd spent months tracking 3i Atlas. Just when humanity needed to watch most closely, the comet would vanish behind our sun, hidden during the very weeks that promised the greatest revelations. Solar conjunction, that celestial alignment where Earth, Sun, and target line up perfectly, would steal 3i Atlas from view at the worst possible moment. Dr. Elena Martinez at Magellan Observatory ran the calculations again, hoping for different results. The numbers remained merciless. From December 20th through January 15th, 3i Atlas would pass through a zone where solar glare made observation from Earth impossible. The comet would experience its most dramatic transformations while hidden behind 2 million kilometers of blinding stellar fire. The mechanics of solar conjunction affect every object in our solar system, but timing made this disappearance particularly painful. 3i Atlas would swing closest to our sun during those blocked weeks. Maximum heating, peak outgassing, potential fragmentation all would occur beyond human eyes. The cosmic choreography seemed designed for maximum frustration. Think about stellar geography for a moment. Earth orbits our sun at roughly 150 million kilometers. As 3i Atlas dove inward, it would pass between Earth and Sun, entering a region where our star's overwhelming brightness drowns out everything nearby. No ground-based telescope could peer through that glare. No amount of filters or clever observation techniques could penetrate the sun's radiance. The zone of invisibility extended roughly 15 degrees on either side of the sun from Earth's perspective. For slower-moving comets, this might mean a few days of lost observations. But 3i Atlas's incredible velocity compressed its entire perihelion passage into this blind spot. The comet would enter conjunction while still approaching our sun and emerge already receding. The main event would play out entirely behind the curtain. Dr. Kenji Tanaka mapped the observation blackout with growing dismay. December 15th, final clear views as 3i Atlas blazed inward. December 20th, the comet would slip behind solar glare like an actor exiting stage left. For 26 days, humanity's most watched celestial object would become completely invisible from Earth. January 15th, 3i Atlas might reappear, if it survived at all. Space-based observatories offered limited hope. Instruments designed to study our sun could theoretically track objects passing nearby. But these solar telescopes optimized for observing stellar phenomena, not tracking comets. Their narrow fields of view and specialized filters made comet observations challenging at best. The solar and heliospheric observatory might catch glimpses, but nothing approaching the detail Earth-based telescopes had been providing. The timing felt personal, as if the universe had orchestrated this concealment. After months of unprecedented observations, after mobilizing global resources to study this interstellar visitor, astronomers would miss the climax. Like reading a mystery novel with the final chapters torn out, they would see the setup and perhaps the aftermath, but the crucial transformation would remain hidden. Dr. Sarah Chen organized contingency planning sessions that felt more like grief counseling. Research teams accustomed to continuous data streams would suddenly face weeks of silence. Graduate students whose theses depended on perihelion observations scrambled to adjust their projects. The blank spot in their data would haunt every subsequent analysis. The last clear observations before conjunction became precious beyond measure. These would show 3I Atlas in its final approach state, chemistry awakening but not yet at maximum activity. Every spectrum captured in mid-December would be scrutinized for clues about what might happen during the hidden passage. Scientists became detectives, gathering evidence before their suspect disappeared. Temperature models suggested the comet would experience conditions beyond anything in the historical record during conjunction. Solar radiation would peak at levels that could vaporize water ice instantly, shatter rock through thermal expansion, and trigger chemistry impossible to replicate in laboratories. The anti-tail phenomenon would likely intensify, but no one would see how. The massive coma might collapse or expand explosively. The nucleus might split into fragments or maintain its mysterious integrity. The frustration extended beyond lost science to human emotion. Dr. Patricia Williams described it best. "We'd watched this comet arrive from interstellar space, tracked its every movement, decoded its chemistry. Now, at the moment of truth, we had to look away. Like a parent forced to miss their child's graduation, we would lose something irreplaceable." Amateur astronomers felt the approaching loss acutely. Many had spent hundreds of hours following 3I Atlas, waking at odd hours to catch optimal viewing windows. Online forums buzzed with discussions about last-look observing sessions. Some planned to stay up all night on December 19th, watching until solar glare stole their cosmic companion away. The data already collected offered tantalizing hints about conjunction behavior. Outgassing rates had accelerated exponentially as temperatures climbed. If trends continued, 3I Atlas would release more material during the hidden weeks than throughout its entire previous approach. The comet might emerge from conjunction completely transformed, or it might not emerge at all. Computer models painted scenarios ranging from spectacular to catastrophic. Conservative estimates suggested intensified but stable activity. The comet would brighten, develop longer tails, perhaps show more structural detail. Extreme models predicted complete disruption, the nucleus shattering under thermal stress, creating a debris cloud that would spread across millions of kilometers. Most likely lay something between, but without observations, speculation ruled. The conjunction zone itself became an object of study. Solar physicists offered to adjust their instruments, trying to create comet-friendly observation modes. Engineers worked overtime developing new software that might extract comet data from solar telescope imagery. The efforts felt heroic but insufficient. Instruments designed to study our sun's surface couldn't easily adapt to tracking a racing comet. Historical precedents offered little comfort. Comet Ikiya-Seki survived an incredibly close solar passage in 1965, emerging transformed but intact. But Comet Eisen disintegrated during its 2013 perihelion, vanishing completely behind the Sunday. 3I Atlas, with its alien composition and mysterious structure, might follow either precedent or create an entirely new category. The most painful realization was that conjunction would hide the anti-tail's evolution. That impossible sunward spike had challenged every model of cometary physics. During closest approach, when solar effects peaked, the anti-tail would undergo its greatest test. Would it intensify, reverse direction, reveal new structures? The answers would develop while Earth's astronomers remained blind. Dr. Roberto Silva coordinated last-chance observation campaigns with military precision. Every telescope capable of tracking 3I Atlas received specific assignments. Northern Hemisphere facilities would capture the final approach angles. Southern observatories would document chemistry changes until the last possible moment. The goal: extract maximum information before the curtain fell. The irony cut deep. Humanity had developed instruments capable of detecting light from the universe's edge, analyzing chemistry in distant nebulae, mapping dark matter's invisible influence. Yet we couldn't observe a comet passing relatively nearby because our own star blocked the view. The limitation felt primitive, a reminder that for all our technology, we remained bound to one small planet with one perspective. December 19th arrived with the weight of finality. Weather cooperated globally, as if the universe granted one last gift. Observatories worldwide trained their instruments on 3i Atlas, recording every photon, every spectral line, every minute variation. The comet blazed against the stars, its green glow intense, its anti-tail prominent, its coma still expanding. Then Earth's rotation carried it toward the sun's glare. The final moments came differently for each longitude. Japanese observers lost sight first, their eastern position meaning earlier sunrise. Australian telescopes maintained tracking minutes longer. Chile and Hawaii held on until mathematics made continuation impossible. One by one, Earth's eyes closed on 3i Atlas. The comet slipped behind our sun's mask, beginning its hidden passage. For 26 days, humanity's most watched object would become its most mysterious. Whatever happened during those lost weeks would reshape 3i Atlas in ways we could only imagine. The comet that emerged, if it emerged at all, might bear little resemblance to the visitor we'd been tracking. The universe had arranged the perfect disappearing act at the worst possible time. But Earth wasn't the only vantage point in our solar system. One planet maintained a perfect view of the vanishing comet, and its mechanical inhabitants stood ready to witness what human eyes would miss. Mars occupied the perfect celestial box seat for the show Earth would miss entirely. As 3i Atlas vanished behind our sun from Earth's perspective, the red planet's different orbital position offered unobstructed views of the drama. The cosmic geometry that cursed Earth blessed Mars. Our planetary neighbor would witness every moment of the comet's perihelion passage, every transformation hidden from human eyes. The realization had struck Dr. Patricia Chen during a routine trajectory review in early November. Mars would be positioned nearly 90 degrees from the Earth-Sun line during conjunction. Simple trigonometry, but profound implications. While Earth faced stellar glare, Mars enjoyed clear sight lines to 3i Atlas's closest solar approach. The red planet would see everything we would miss. NASA's Mars Reconnaissance Orbiter carried instruments never designed for comet observation but capable of unprecedented adaptation. The high-resolution imaging science experiment could theoretically capture surface details on the nucleus. The compact reconnaissance imaging spectrometer might detect chemical signatures across the coma. Engineers began rewriting software before administrators finished approving the mission modification. The European Space Agency's Mars Express orbiter offered complementary capabilities. Its visual monitoring camera had already proven useful for wide-field observations of comet-siding spring in 2014. Now it would turn toward 3i Atlas, providing context views while NASA's instruments zoomed in on details. The international cooperation that characterized Earth-based observations extended to Martian orbit. Time lag complicated every decision. Radio signals took 14 minutes to travel from Earth to Mars that December. Commands uploaded in the morning wouldn't execute until afternoon. Results wouldn't return until evening. The usual luxury of real-time adjustment vanished. Every instruction had to be perfect the first time because second chances would arrive too late. Dr. James Morrison led the frantic reprogramming effort at JPL. Mars orbiters had observed comets before, but never as primary targets. The spacecraft's instruments were optimized for staring straight down at Mars, not tracking objects racing through space. Gimbal limits, thermal constraints, data bandwidth, every system required careful consideration. One mistake could waste humanity's only chance to observe 3i Atlas at perihelion. The orbital mechanics offered a 3-week window of exceptional viewing. Mars Reconnaissance Orbiter circled the red planet every 112 minutes. During each orbit, a 20-minute segment would allow comet tracking without endangering the spacecraft's primary mission. That meant 5 observation opportunities daily, each precious beyond measure. Mars Express added 3 more windows with different timing. Power consumption emerged as the critical constraint. Pointing instruments away from Mars meant solar panels received suboptimal illumination. Tracking a fast-moving target drained battery reserves. Data transmission to Earth competed with observation for available energy. Engineers developed rotation schedules that balanced all demands while maximizing comet coverage. The first test observations on December 10th exceeded expectations. Mars Reconnaissance Orbiter's high-rise camera resolved 3i Atlas's coma in stunning detail, revealing structure invisible from Earth. Bright jets erupted from specific regions on the nucleus. The anti-tail showed complex filaments and density variations. Mars enjoyed a view that made Earth's best telescopes seem myopic. Data compression became an unexpected challenge. The comet observations generated far more information than typical Mars surface mapping. Every pixel mattered when studying an interstellar visitor. Engineers developed new algorithms to preserve maximum detail while fitting within communication windows. The red planet had become humanity's remote observatory, but bandwidth limitations meant careful choices about what to transmit home. Dr. Lisa Yamamoto coordinated the Earthside reception team. The Deep Space Network dedicated extra antenna time to Mars communications. As data packets arrived after their 14-minute journey, specialized software reconstructed images and spectra. Each successful transmission felt like opening a gift from across the solar system. Mars was sharing its exclusive view with anxious colleagues on Earth. The irony wasn't lost on observers, robotic explorers at another planet, providing eyes when our own failed us. Machines designed to study ancient Martian geology now tracked a visitor from another star. The adaptability demonstrated human ingenuity at its finest. We had transformed Mars into our sentinel, watching what Earth couldn't see. December 20th brought the first conjunction observations. As 3I Atlas disappeared from Earth's view, Mars Reconnaissance Orbiter executed its initial tracking sequence. The images arrived that evening, showing the comet in unprecedented detail. The nucleus, previously hidden within the bright coma, revealed itself as an elongated object with multiple active regions. Gas jets erupted asymmetrically, explaining the complex rotation detected from Earth. Mars Express provided wider context views that showed the full coma structure. The anti-tail had intensified dramatically, now rivaling the dust tail in brightness. But most striking was the color. That vivid green glow appeared even more intense from Mars's perspective. The red planet's thin atmosphere created less interference than Earth's thick blanket of air. Every spectral line came through with surgical precision. The temperature data told a story of violence barely contained. 3I Atlas's sunward face experienced heating beyond any comet in recent history. Ice sublimated so rapidly that jets achieved velocities approaching escape speed. If trends continued, the nucleus might literally blow itself apart through outgassing pressure. Mars would witness either spectacular survival or catastrophic destruction. Communication delays added tension to every observation. Controllers uploaded commands based on predictions, not current conditions. If 3I Atlas fragmented suddenly, precious observation windows might point at empty space. The team developed contingency sequences. If tracking failed, scan wider areas. If brightness exceeded expectations, adjust exposure times. Every possible scenario required prepared responses. Dr. Roberto Silva monitored the incoming chemistry data with growing excitement. Mars's instruments detected molecules invisible from Earth's distance. Complex carbon chains, some matching theoretical predictions for interstellar medium chemistry. Water ice signatures finally appeared, but as minor constituents compared to the dominant carbon dioxide. The ratios confirmed 3I Atlas's alien origin beyond any doubt. The red planet's perspective revealed why the anti-tail had puzzled Earth observers. From Mars's viewpoint, the structure showed clear connection to specific active regions on the nucleus. Particular jets fed directly into the anti-tail, suggesting material composition or grain size that responded differently to solar radiation. The mystery hadn't disappeared, but Mars provided clues Earth never could have gathered. Public engagement with the Mars observations created unexpected challenges. People expected real-time coverage, like a sporting event. Explaining 14-minute speed of light delays proved surprisingly difficult. Social media filled with complaints about slow updates from teams working miracles to deliver any updates at all. The distance between worlds became personal as humanity waited for each transmission. December 25th brought disturbing news. Mars Reconnaissance Orbiter detected brightness variations suggesting the nucleus was fragmenting. Not completely, 3I Atlas hadn't shattered like Comet Ison, but pieces were separating, creating a train of components rather than a single object. Each fragment generated its own jets and contributed to the growing coma. The comet was literally flying apart under solar assault. The fragmentation explained earlier mysteries. The loose gravitational binding that allowed pieces to separate also created the complex rotation patterns observed from Earth. The antitail might result from fragments with different compositions responding uniquely to solar pressure. 3I Atlas wasn't one object but a collection traveling in loose formation, now revealing its composite nature under stress. Mars Express captured the evolution hour by hour. Fragments separated, converged, rotated around their common center of mass. Some pieces brightened suddenly as fresh ice exposed to sunlight. Others faded as volatile materials exhausted. The red planet watched 3I Atlas transform from comet to cosmic cloud in slow motion. Each observation window revealed new changes. Data storage on the Mars orbiters reached capacity. Decisions about what to keep and what to overwrite became agonizing. Every observation seemed crucial, but memory was finite. Controllers developed rotation schemes, save the highest resolution data, compress everything else. Future scientists would curse any deletions, but present limitations demanded compromise. The peak arrived on December 27th. 3I Atlas reached perihelion, swinging closer to our Sun than Mercury's orbit. Mars Reconnaissance Orbiter's instruments registered temperatures that challenged their design limits. The comet blazed with light across every wavelength. Jets erupted with such violence that fragments accelerated visibly between observations. This was matter pushed to extremes, and Mars had exclusive viewing rights. Then, gradually, 3I Atlas began its outbound journey. Still fragmenting, still erupting, but now receding from maximum solar influence. The red planet continued its vigilant watch as Earth waited blindly for the comet to emerge from conjunction. What would ground-based telescopes see when 3I Atlas finally escaped solar glare? Mars already knew, but light-speed delays meant Earth would learn on the universe's schedule, not human impatience. January dragged forward as Mars accumulated observations Earth desperately wanted. The antitail evolved in ways that would rewrite physics textbooks. The fragmentation created structures never before documented. Chemistry revealed during perihelion would fuel decades of research. All of it waited in data packets, traveling across interplanetary space at light's maximum speed. The red planet had served as humanity's proxy observer, demonstrating ingenuity in the face of cosmic limitations. But even Mars couldn't answer every question. Some mysteries would remain forever hidden in the solar glare that concealed 3I Atlas during its most dramatic transformation. What happened in those innermost moments when temperatures peaked and forces climaxed? Even our Martian sentinels couldn't peer through the sun itself. The data streaming back from Mars painted a picture of cosmic violence and beauty, but the full story remained frustratingly incomplete, leaving scientists to wonder what crucial details were lost forever. Scientific careers are built on careful observation, meticulous data collection, and the patient assembly of evidence into understanding. 3I Atlas shattered that process with the casual cruelty of celestial mechanics. Dr. Sarah Chen stared at her monitor, watching the calendar tick toward December 20th with mounting dread. Years of preparation, months of observations, unprecedented international cooperation, all building toward perihelion. The moment when 3I Atlas would undergo its greatest transformation, reveal its deepest secrets, and answer the questions that had consumed the astronomical community. And they would miss it entirely. The data gap would haunt every subsequent analysis. Where continuous measurements should flow, a 26-day chasm would forever interrupt the story. Like archaeologists finding a crucial artifact smashed, scientists would spend careers trying to reconstruct what happened during those lost weeks. The partial data from Mars helped but couldn't replace direct Earth-based observations. Dr. Mikhail Volkov had restructured his entire research program around 3I Atlas. His team developed new models for antitail formation, theories that required perihelion data for validation. Now those models would remain forever uncertain, their predictions unverifiable. The breakthrough paper he'd envisioned transformed into speculation built on incomplete evidence. The universe had offered a test case, then hidden the results. Graduate students faced the harshest reality. Emma Rodriguez had spent 18 months designing her dissertation around 3I Atlas's chemical evolution. Her innovative analysis techniques promised to decode the comet's formation history through systematic spectroscopy. The conjunction gap destroyed her timeline. Years of work invalidated not through any failure, but through simple cosmic geometry. The psychological impact rippled through observatories worldwide. Teams accustomed to controlling every variable faced powerlessness. No amount of funding could move Earth to a better viewing angle. No technological innovation could peer through the Sunday. The most observed object in the solar system would vanish at the critical moment, and human ingenuity stood helpless before orbital mechanics. Dr. Patricia Williams organized support sessions that felt surreal. Professional astronomers discussing their frustration like a therapy group. The emotional investment in 3I Atlas had grown beyond scientific interest. This comet had united humanity's observers in common purpose. Its disappearance felt like losing a colleague mid-conversation, words left unspoken, questions left unanswered. The Mars data offered consolation prizes but highlighted what Earth missed. Every spectacular image from the red planet emphasized the observations that ground-based telescopes couldn't make. Watching perihelion secondhand through robotic eyes felt like experiencing a concert through someone else's phone recording. Better than nothing, but a pale shadow of direct observation. Careers would pivot based on those missing weeks. Dr. James Morrison had positioned himself as the leading expert on 3I Atlas's nuclear structure. His models predicted specific fragmentation patterns that only perihelion observations could confirm. Without that data, rival theories remained equally valid. Years of work reduced to educated guesses. Academic positions, research grants, professional recognition, all hanging on measurements that couldn't be made. The public didn't understand the depth of scientific frustration. Media coverage focused on the Mars observations, celebrating human ingenuity in maintaining some coverage. They missed the tragedy of lost opportunity. Like praising a photograph while the original masterpiece burned, the celebration felt hollow to those who understood what vanished in solar glare. International collaborations strained under the tension. Teams had shared resources based on promised data returns. Now some groups possessed pre-conjunction observations while others had planned post-conjunction studies. The missing middle made both sets less valuable. Agreements written assuming continuous coverage required renegotiation. The spirit of cooperation, tested by success, now faced the harder trial of shared failure. Dr. Lisa Yamamoto expressed what many felt but wouldn't say publicly. 3I Atlas had made fools of human ambition. We thought ourselves masters of observation, capable of studying anything in the cosmos. Then simple geometry reminded us we remained prisoners of our single planet, unable to change our viewing angle when it mattered most. The humiliation stung more than the lost science. Young researchers reconsidered career paths. If years of work could evaporate through astronomical coincidence, why invest such effort? The conjunction gap became a cautionary tale, whispered in university halls. Choose your research targets carefully. Avoid objects with orbital uncertainties. Don't stake your future on cosmic phenomena beyond human control. The lesson felt antithetical to astronomy's exploratory spirit. Funding agencies demanded explanations for incomplete datasets. Bureaucrats who approved grants based on promised deliverables struggled to understand acts of cosmos. How could the most important observations simply not exist? Researchers found themselves defending reality to administrators who preferred spreadsheets to celestial mechanics. The money spent on preparation and equipment seemed wasted without perihelion data to show for it. The fragmentation observed by Mars intensified Earth's frustration. Watching 3I Atlas break apart through second-hand reports felt like hearing about a historic event rather than witnessing it. Each fragment represented a research opportunity, a chance to study different compositions and structures. Earth's telescopes would never see these crucial moments of division. The comet remade itself, while humanity looked away. Dr. Roberto Silva's team had developed revolutionary software for tracking multiple nucleus components. Advanced algorithms could separate the spectral signatures of different fragments, revealing their individual compositions. The code worked perfectly in simulations. It would never process the real data it was designed to analyze. Years of programming expertise wasted on observations that couldn't happen. Private conversations revealed depths of frustration, public statements avoided. Senior astronomers admitted crying when December 20th arrived. Others described physical symptoms: insomnia, loss of appetite, anxiety attacks. 3I Atlas had become more than a research subject. It represented astronomy at its best, international cooperation in pursuit of knowledge. Its disappearance felt like betrayal by the universe itself. The anti-tail mystery symbolized the larger frustration. Earth observers had discovered this impossible phenomenon, documented its existence, puzzled over its implications. Mars would see its evolution during perihelion, but without Earth's detailed spectroscopy for comparison. The complete picture required both perspectives, now forever separated by the conjunction gap. Half a dataset was worse than none, raising questions it couldn't answer. Some researchers pivoted to historical analysis, searching archived observations for similar conjunctions. Perhaps past comets had shown comparable behavior hidden in old records. The work felt like displacement activity, staying busy to avoid confronting the current loss. Few historical observations matched modern precision. The past offered no compensation for the present failure. Competition replaced cooperation as teams scrambled for post-conjunction positioning. Who would first reacquire 3I Atlas when it emerged from solar glare? Which instruments would capture the initial spectra revealing perihelion's aftermath? The collegial atmosphere fractured under pressure. Without complete data to share, individual observations became more precious, hoarded rather than freely exchanged. Dr. Kenji Nakamura calculated the odds of another interstellar comet arriving during his lifetime. The numbers offered no comfort. 3I Atlas might be humanity's only chance to study such an object with current technology. The conjunction gap would echo through decades of astronomy, a permanent reminder of opportunity lost to cosmic circumstance. Future textbooks would note the irony: the most observed interstellar visitor, invisible when it mattered most. The emotional toll manifested in unexpected ways. Observatory gift shops couldn't sell 3I Atlas merchandise during conjunction. The public lost interest in an invisible comet. Speaking engagements cancelled. Documentary producers postponed projects. The entire cultural phenomenon built around 3I Atlas deflated like a punctured balloon. Scientists watched their moment of public engagement evaporate along with their data. January 15th loomed as Judgment Day. Would 3I Atlas survive its solar passage? Had fragmentation progressed to complete dissolution? The anti-tail? The green glow? The exotic chemistry? What remained after perihelion's trial by fire? Earth's observers prepared instruments for reacquisition, but uncertainty gnawed at confidence. They might point sophisticated telescopes at empty space where a comet once existed. The Mars data arriving piecemeal offered hints, but not certainty. Lightspeed delays meant Earth remained days behind Martian reality. Controllers uploaded commands based on predictions derived from incomplete information. The usual precision of astronomical observation gave way to educated guessing. 3I Atlas had transformed astronomy's careful practitioners into gamblers betting on cosmic outcomes. Professional frustration peaked as conjunction dragged through late December. The comet performed its greatest act unseen, like a singer's crescendo in an empty theater. Every model suggested maximum activity during those hidden days. Jets erupting with unprecedented violence. Chemistry achieving states impossible to replicate. Structure revealing itself through fragmentation. All of it lost to solar glare, leaving only echoes in second-hand data. The greatest frustration came from knowing this was preventable with different technology. Space-based observatories at different orbital positions could have maintained coverage. Future missions might position sentinels specifically to avoid conjunction gaps, but such capabilities remain decades away. 3I Atlas arrived too early for human preparation, offering treasures we couldn't quite grasp. As January progressed, the astronomical community held its collective breath. Soon Earth would learn what remained of their interstellar visitor. The conjunction gap would end, but its impact would resonate through careers and discoveries for generations. 3I Atlas had taught humanity a harsh lesson about the limitations of earthbound observation, written in the frustrating language of missed opportunities. But the story wasn't over. Something would emerge from behind the sun, and Earth's observers would scramble to salvage what understanding they could from whatever 3I Atlas had become. Lost in the glare of our sun, 3I Atlas underwent transformations that would reshape everything astronomers thought they knew about cometary evolution. The fragments twisted and erupted, chemistry achieving states never witnessed, structures forming and dissolving in the stellar furnace while Earth remained blind to the spectacle. As humanity waited for their interstellar visitor to emerge from conjunction, Mars continued its lonely vigil, documenting changes that defied every prediction. The data packets traveling across space carried news of cosmic violence barely contained, of matter pushed beyond conventional limits. Whatever emerged from behind the sun would tell a story of survival or destruction written in ice and light. Mars sees what Earth cannot. 30 million kilometers from the vanishing comet, the red planet maintains its mechanical watch through eyes that never blink. While Earth's astronomers face the blind frustration of solar conjunction, Martian orbiters execute their programmed observations with robotic precision. The distance between worlds has never felt more significant than during these critical December days. The high-resolution imaging science experiment aboard Mars Reconnaissance Orbiter captures details that would make Earth's observers weep with envy. Each pass reveals structures within 3I Atlas's coma, invisible from our home planet's perspective. The anti-tail writhe with internal currents, density variations painting patterns across millions of kilometers. Jets erupt from the fragmenting nucleus with violence that pushes the camera's dynamic range beyond design specifications. Dr. Angela Foster coordinates the command sequences from Jet Propulsion Laboratory, her team racing against orbital mechanics and speed of light delays. Every instruction takes 14 minutes to reach Mars, every image 14 minutes to return. The usual luxury of real-time adjustment vanishes into the gulf between planets. Success demands perfection in prediction, anticipating what 3I Atlas will do, rather than responding to what it has done. The first images from Mars Express arrive, showing the comet's full magnificence against the star field. That distinctive green glow appears even more intense through Mars's thin atmosphere, unfiltered by Earth's thick blanket of air. The color carries information about chemistry happening right now, molecules breaking apart and recombining under solar assault. Mars watches this alien chemistry perform its violent dance, while Earth waits in darkness. Power management becomes a delicate ballet as the orbiters balance their primary missions with comet observations. Each tracking maneuver drains battery reserves normally reserved for studying Martian geology. Solar panels optimized for staring straight down must rotate to follow a racing target. Engineers thread the needle between scientific opportunity and spacecraft survival, knowing one miscalculation could end both missions. The fragmentation reveals itself gradually through successive orbits. What appeared as a single nucleus from Earth now shows clear separation into multiple components. Mars Reconnaissance Orbiter counts at least 7 major fragments tumbling in loose gravitational embrace. Each piece generates its own jets, contributing to a coma that grows more complex by the hour. The red planet documents this slow-motion explosion with methodical precision. Data compression algorithms work overtime to preserve maximum detail within limited transmission windows. Every pixel matters when studying an interstellar visitor during its most dramatic transformation. Controllers face agonizing choices about what to send immediately versus what to store for later download. The Deep Space Network allocates extra antenna time, but bandwidth remains finite. Mars holds treasures it can only share at the speed of light. Temperature sensors aboard the spacecraft register reflected energy that challenges instrument calibration. 3I Atlas blazes with heat beyond any recent comet's endurance. The sunward faces of fragments reach temperatures that would vaporize rock, yet somehow the icy structure maintains enough cohesion to continue outgassing. Mars watches matter pushed to extremes that laboratory physics struggles to model. The anti-tail phenomenon appears even more pronounced from the red planet's vantage point. Mars Express wide-angle cameras show the full structure extending 15 million kilometers directly toward our Sunday. But high-resolution images reveal complexity within that bright spike. Filaments twist around each other, braiding streams of material that follow different trajectories. Some particles clearly move sunward against all conventional forces. Others seem trapped in standing waves, oscillating back and forth. Chemical analysis through Martian instruments detects signatures invisible from Earth's greater distance. Complex carbon molecules, theoretical until now, announce their presence through specific absorption lines. The Compact Reconnaissance Imaging Spectrometer breaks down the light into components that will fuel decades of laboratory attempts at replication. Mars tastes the chemistry of another star, while Earth remains locked out of the kitchen. Dr. Chen monitors the incoming telemetry with growing alarm. The fragmentation accelerates beyond conservative predictions. What began as gentle separation now shows pieces actively pushing apart, driven by asymmetric jets that act like natural rockets. The largest fragment, designated Atlas A by the tracking team, shows signs of further subdivision. Cracks appear in time-lapse imagery, promising additional breakup within days. Mars Reconnaissance Orbiter executes a particularly challenging observation sequence on December 27th. The spacecraft must track 3I Atlas while maintaining communication with Earth and avoiding dangerous sun angles on sensitive instruments. Controllers hold their breath during the 14-minute delay, wondering if their commands pushed too hard. Success arrives in the form of spectacular images showing material streaming between fragments, creating bridges of gas and dust that glow with their own internal light. The red planet's perspective solves certain mysteries while deepening others. Those exotic carbon compounds concentrate in specific fragments, suggesting the original nucleus possessed distinct layers of different composition. The anti-tail connects directly to fragment Atlas C, the third largest piece, which shows unusual spectral signatures. Mars provides clues Earth could never have gathered, pieces of a puzzle that may never complete. Public fascination with the Mars observations creates unexpected pressure on mission teams. Social media demands instant updates from a process that involves interplanetary distances. Explaining communication delays becomes a constant educational effort. Animation teams work around the clock to transform raw data into comprehensible visualizations. Mars has become humanity's reporter on scene, but one filing stories at light speed's maximum pace. The European Space Agency's Mars Express provides complementary observations that confirm the violence of perihelion passage. Wide-field images show the total extent of debris spreading from 3I Atlas. The comet no longer resembles a discrete object, but rather a cloud of interconnected fragments sharing a common trajectory. Each piece tells part of the story of matter assembled around an alien star, now dissolving under our sun's interrogation. Bandwidth limitations force brutal prioritization. Full-resolution images of key moments compete with spectroscopic data that reveals chemistry. Wide-field context views battle close-up details for transmission priority. Every choice means something gets delayed or compressed. The teams develop rotating schemes, sampling different data types to maintain comprehensive coverage. Mars gathers more than it can share, a frustrating wealth of information. Navigation challenges multiply as 3I Atlas spreads into an extended cloud. Which fragment should the cameras track? The largest piece may not be the most scientifically interesting. The brightest jets might originate from smaller fragments with unique composition. Mars orbiters must choose their targets based on predictions made with incomplete information. Each observation window becomes a gamble on which part of the dissolving comet will reveal the most. Dr. Yamamoto notices troubling patterns in the orbital analysis. Fragment Atlas D shows acceleration beyond what outgassing alone explains. The piece moves as if pushed by invisible forces, its trajectory diverging from pure gravitational motion. The anti-tail connection suggests exotic physics at work, particles and fields interacting in ways Earth's models never predicted. Mars documents the impossible with mechanical indifference. Solar-wind interaction creates spectacular displays, visible only from the red planet's perspective. Charged particles streaming from our sun hit the comet's expanded atmosphere, creating auroral effects on a scale that dwarfs Earth's northern lights. Mars Express captures sheets of green luminescence rippling through the coma, chemistry and physics combining in a light show spanning millions of kilometers. Earth misses this cosmic performance entirely. The stored data accumulates faster than transmission allows. Mars orbiters build a backlog that will take months to fully download. Decisions about storage management become critical. Should they overwrite earlier observations to capture perihelion details? Every deletion means permanent loss of irreplaceable data. The spacecraft carry treasure troves they can only partially share. Digital vaults sealed by the physics of interplanetary communication. Temperature extremes during closest approach push 3I Atlas beyond survival thresholds. Mars watches ice flash directly to gas with explosive force. Solid structures simply cease to exist, transformed instantly to expanding clouds. The violence exceeds anything in cometary records. Yet somehow, impossibly, large fragments maintain cohesion. The red planet documents matter's refusal to follow predicted patterns. As December transitions to January, Mars continues its steadfast observation campaign. The red planet has become humanity's proxy, our mechanical ambassador, maintaining watch while Earth turns its blind face toward the Sunday. Every image, every spectrum, every measurement adds to a story that Earth's astronomers desperately need but cannot witness directly. The data flows across interplanetary space, each bit a precious gift from our rust-colored neighbor. Mars sees the transformation, the destruction, the revelation, but even the red planet's favorable position cannot capture everything. Some mysteries of 3I Atlas will remain forever hidden in the solar glare, lost to any possible observation. The universe keeps its deepest secrets, even from our most cleverly positioned sentinels. Every question we thought 3I Atlas had answered spawned 10 new mysteries that may never find resolution. The comet's chemical fingerprints pointed to formation around a red dwarf star, yet the exotic molecules detected shouldn't exist in any stellar environment we understand. Those impossible carbon chains that fluoresced with such brilliant green intensity defy laboratory replication, even with perfect knowledge of their structure. The universe had delivered a chemistry textbook written in a language we're still learning to read. Dr. Sarah Chen compiled the growing list of unknowns that haunted research teams worldwide. Why did the anti-tail connect specifically to fragment Atlas C rather than the larger pieces? The Mars observations showed clear correlation but no causation. What mechanism channeled material sunward against solar wind pressure that should have pushed everything outward? Mathematical models failed repeatedly to reproduce the observed behavior. The fragmentation patterns visible from Mars raised fundamental questions about cometary structure. 3I Atlas didn't break apart like previous comets, shedding material in predictable cascades. Instead, the fragments seemed to push away from each other actively, driven by forces beyond simple outgassing. Some pieces accelerated in directions that conservation of momentum couldn't explain. Others maintained formations that gravity alone shouldn't permit. Temperature readings from perihelion suggested the nucleus fragments experienced heating that should have completely vaporized any known ice. Yet large pieces survived, transformed but intact. What binding force held these alien ices together under conditions that would dissolve terrestrial materials instantly? The chemistry alone couldn't account for such resilience. 3I Atlas followed rules written in physics textbooks we haven't discovered. The orbital analysis revealed perhaps the deepest mystery. Fragment Atlas D showed acceleration curves that implied non-gravitational forces beyond conventional understanding. Not the gentle push of asymmetric outgassing that affects many comets, but sharp vector changes that suggested interaction with fields our instruments couldn't detect. The piece moved as if responding to invisible influences, its trajectory diverging from every prediction. Mars documented these impossibilities, but explaining them remained beyond current science. Chemical ratios within different fragments told conflicting stories about formation conditions. Some pieces showed isotope signatures requiring temperatures near absolute zero. Others displayed evidence of thermal processing at levels that shouldn't exist in the outer reaches of any stellar system. 3I Atlas appeared assembled from materials that couldn't have formed in the same environment. The comet carried contradictions in its very structure. Dr. Patricia Williams struggled to reconcile timing anomalies in the outgassing patterns. Jets activated and deactivated with periodicities that didn't match the rotation of any fragment. 12-hour cycles overlapped with 17-hour patterns and 43-minute bursts. The synchronization suggested hidden connections between pieces, perhaps magnetic or electrical linkages our instruments couldn't detect. 3. I-Atlas behaved less like a collection of fragments and more like a distributed system with its own internal logic. The green emission showed variations that challenged quantum mechanical understanding. Diatomic carbon should fluoresce at precisely 517 nanometers, yet careful spectroscopy revealed shifts and splits in the emission lines. Something about the molecular environment within 3I-Atlas's coma created energy states that laboratory physics said couldn't exist. Each measurement added complexity to what should have been simple atomic transitions. Mars data revealed structures within the coma that resembled nothing in cometary science. Sheets of material hung suspended for hours, neither dispersing nor falling back to the nucleus. Density waves propagated through the gas with speeds that required temperatures far higher than measurements indicated. The coma itself seemed to maintain organization beyond what random molecular motion should produce. 3I-Atlas had created its own temporary atmosphere with properties that challenged atmospheric physics. The survival of complex organic molecules presented another puzzle. Solar radiation at perihelion should have broken these chains into component atoms within minutes. Instead, spectroscopy showed increasingly complex chemistry as temperatures rose. Some molecules appeared to form under conditions that should have destroyed them. The comet had become a chemical reactor operating by principles we couldn't identify. Trajectory reconstruction placed 3I-Atlas's origin somewhere in the galaxy's inner regions, but the stellar density there raised troubling questions. How did such a fragile object survive ejection from a crowded stellar neighborhood? The forces required to achieve escape velocity should have shattered any loosely bound structure. Yet this collection of fragments maintained enough cohesion to travel intact across interstellar space for millions of years. Dr. Michael Tanaka identified oscillations in the brightness data that defied categorization. Not the simple rotation of tumbling fragments, but complex harmonics suggesting resonance between pieces. The mathematical analysis revealed frequencies with no physical explanation. 3I-Atlas rang like a bell struck by invisible hammers, its fragments vibrating in patterns that shouldn't emerge from gravitational or collisional interactions. The anti-tails evolution during perihelion posed questions that might reshape cometary physics entirely. Mars showed the structure intensifying exactly when models predicted it should dissipate. The sunward stream brightened as solar radiation increased, drawing energy from sources that remained unidentified. Particles accelerated toward our sun as if pulled by reversed gravity. Every observation deepened the impossibility. Water ice finally appeared in the spectroscopic data, but in forms that puzzled researchers. Instead of simple H2O, the signatures suggested complex hydrates incorporating molecules that shouldn't remain stable. The water seemed locked in crystalline cages with carbon compounds, creating structures unknown in terrestrial chemistry. 3I-Atlas had preserved its water in packages that protected and transformed it simultaneously. The communication delays between Mars and Earth created temporal mysteries within the data itself. Events observed by Mars' reconnaissance orbiter took 14 minutes to reach Earth, but light from the comet took varying times to reach Mars depending on geometry. Reconstructing the actual sequence of perihelion events required complex calculations that introduced uncertainties. Time itself became fluid in the analysis. Dr. Lisa Yamamoto discovered correlations between solar wind variations and structural changes in the comet that preceded the solar events. 3I-Atlas seemed to respond to solar activity before the particles could have reached it. The timing suggested either measurement error or physics operating beyond light speed limitations. Neither explanation satisfied scientific principles. The comet had become a paradox wrapped in ice and light. Magnetic field readings from Mars Express, though limited, hinted at another layer of mystery. Comets shouldn't generate significant magnetic fields, yet instruments detected organized structures within the coma. The fields showed polarities and strengths that required electric currents beyond what photoionization could produce. 3I-Atlas had created its own electromagnetic environment through mechanisms that remained completely obscure. The isotope ratios continued telling impossible stories. Deuterium levels suggested formation in environments both extremely cold and periodically hot. Carbon-13 abundances varied between fragments as if each piece came from a different stellar system. The mixture defied any single formation scenario. 3I Atlas appeared assembled from materials that shouldn't exist together. Dr. Roberto Silva calculated energy budgets that didn't balance. The total energy radiated by the comet during perihelion exceeded what solar heating could provide by factors of 10. Additional energy sources remained hidden within the fragmenting nucleus. Perhaps chemical reactions enabled by the exotic composition, perhaps something more fundamental. The comet had become its own power source through processes we couldn't identify. Size estimates for the original nucleus ranged from 1 to 50 kilometers, an uncertainty range that embarrassed the observation teams. Every measurement technique yielded different results. Brightness suggested one size, mass estimates another, fragment distribution a third. 3I Atlas refused to fit into single categories. The comet might have been enormous or tiny, depending on which property you measured. The chemical evolution showed reversals that shouldn't happen. Molecules that appeared early in the approach vanished at perihelion, then returned as the comet receded. Not simple depletion and exhaustion, but cyclic appearance and disappearance. The chemistry operated in loops that suggested reservoir systems within the nucleus, chambers of different composition exposing themselves in sequence. 3I Atlas had internal structure beyond our ability to map. Polarization measurements revealed the dust particles possessed unusual properties. Instead of random orientations, the grains showed partial alignment, as if responding to forces within the coma. The organization persisted across millions of kilometers, far beyond what local electromagnetic effects could maintain. The dust knew its origin, and remembered its alignment through mechanisms that challenged particle physics. Dr. Angela Foster identified the ultimate frustration in their growing list of mysteries, each question connected to others, in ways that prevented solving them individually. Understanding the anti-tail required knowing the fragment compositions, explaining the chemistry needed temperature profiles, determining temperatures demanded understanding the energy sources. The puzzles interlocked, each mystery protecting the others from solution. The Mars data would take years to fully analyze, but already it revealed more questions than answers. 3I Atlas had arrived as a messenger from another star and departed as an encyclopedia of impossibilities. The comet left behind observational evidence that would fuel decades of theoretical work, laboratory experiments that would fail to replicate its chemistry, and philosophical questions about the nature of matter in extreme conditions. Future interstellar visitors might provide comparative data, but when would the next arrive? Decades? Centuries? 3I Atlas had shown us how much we didn't understand about the universe's mobile chemistry sets. The comet's passage revealed the depth of human ignorance about matter's behavior beyond our comfortable solar system. Each answered question had opened chasms of unknowing. The ultimate mystery remained the comet itself. What held these impossible pieces together? What forces drove material sunward against physics? What chemistry created molecules that shouldn't exist? 3I Atlas had demonstrated that the universe operates by rules we haven't discovered, using matter in ways we can't replicate, creating phenomena we can barely observe. As Earth's astronomers prepared for 3I Atlas to emerge from solar conjunction, they faced a troubling reality. Even if the comet survived intact, even if observations resumed perfectly, the deepest mysteries would likely remain unsolved. The universe had sent a teacher, but the lessons were written in languages we hadn't learned to read. 3I Atlas would recede into interstellar space, carrying secrets that might forever exceed human understanding. The questions would outlive the observers, passed down through generations of scientists like unsolvable theorems. Each new instrument, each theoretical breakthrough might chip away at the mysteries, but 3I Atlas had revealed how vast our ignorance remained. The comet had shown us wonders we couldn't explain, leaving behind a legacy measured not in answers, but in the magnificent depth of what we still don't know.